Every secret on the internet, your bank records, classified military communications, your private messages, is locked inside a mathematical vault. We trust this vault because opening it requires solving a math problem so difficult that a classical supercomputer would need billions of years to crack it. But what if the lock is fundamentally flawed? What if you could use a mathematical loophole to bypass the door entirely? In 1994, a mathematician named Peter Shor discovered that loophole. He proved that a theoretical machine, a quantum computer, could shatter many of our global encryption system not in a billions of years, but potentially in hours. Today, we are going to look under the hood. I'm going to break down the exact mathematics behind Shor's algorithm, step by step, and why the governments around the world are racing to defend against it. This is Elaxior, Science Visualized. To understand how Shor's algorithm picks the lock, we first have to understand the lock itself. Much of the internet relies on RSA encryption, which is based on a mathematical problem called prime factorization. Multiplication is easy. If I multiply two large prime numbers together, a computer can do it almost instantly. For example, 7919 into 6841 equals this number. But now imagine I hand you that final number and ask, which two prime numbers created it? No efficient classical algorithm is known for solving this problem when the number becomes extremely large. A modern RSA key uses numbers hundreds of digits long. For sufficiently large keys, even the best known classical algorithms would require an astronomical amount of computation, far beyond anything we can realistically achieve. This giant number, let's call it n, is the public lock. The two secret prime numbers are the key. For decades, mathematicians searched for a shortcut. Eventually, they discovered something surprising. Factoring can be transformed into a completely different problem. Instead of finding prime numbers directly, we can search for a repeating pattern using modular arithmetic, sometimes called block math. Let's keep the numbers tiny so we can see the math. Suppose our public lock n is 15. Our goal is to recover its prime factors. Mathematicians discovered a special function, a to the power x modulus of n. Now we choose a number smaller than 15. Let's pick 7. This is our value of a. We raise 7 to different powers and keep only the remainder after dividing by 15. 7 to the power 0 equals 1. Dividing by 15, we get 1. We start with x equals 0 and get a remainder of 1. Then we plug in larger and larger values of x. The remainder becomes 7, then 4, then 13, and then we are back to 1 again. The moment we return to where we started, we have discovered a repeating cycle. If we keep going, the sequence repeats. We found a loop. The number of steps required for the pattern to repeat is called the period, represented by r. In this case, r is 4. Now comes the remarkable part. If certain mathematical conditions are satisfied, and in this example they are, we can use the period to recover the factors of 15. We compute a to the power r by 2 plus minus 1, substituting our values, which becomes 7 square plus minus 1, and we get 50 and 48. Now find the greatest common divisor between those numbers and our original log. Greatest common divisor of 50 and 15 gives 5. Similarly, 48 and 15 gives 3. Boom! 3 and 5 are the secret prime numbers. We cracked the log. So why doesn't this break the internet today? Because of the scale. When n contains hundreds of digits, the repeating pattern becomes unimaginably large. A classical computer still has to perform an enormous amount of work to discover the period. For sufficiently large RSA keys, the computation becomes impractical. In 1994, Shor realized that a quantum computer could find this period dramatically faster than any classical method. A classical computer uses bits, zeros and ones. A quantum computer uses qubits. Thanks to superposition, a qubit can exist in a combination of 0 and 1 at the same time. Shor's insight was to place a large collection of qubits into a superposition representing many possible values of x simultaneously. The quantum computer then evaluates our function for all of those values at once. Instead of checking possibilities one by one, the machine creates a quantum state that contains information about the entire repeating structure of the function. Problem solved. We just look at the computer and get the period. No. The moment we measure a quantum state, the superposition collapses. All that rich quantum information disappears, leaving us with only one random single outcome. So how do we extract the hidden period without destroying it? This is where Shor's real breakthrough appears. Interference. When you play a chord on piano, multiple sound waves combine together. The mathematical tool used to reveal the hidden frequencies inside that sound is called a Fourier transform. Shor realized that period we are searching for behaves like a hidden frequency buried inside a massive collection of numbers. So before measuring the quantum state, he applies a remarkable operation called the quantum Fourier transform or QFT. The QFT converts the hidden period structure of the function into a new pattern that contains information about the period. During this process, quantum interference occurs. Some possibilities cancel each other out through the destructive interference, others reinforce each other by constructive interference. The result is probability distribution with strong peaks at values closely related to the hidden periods. The QFT acts like a frequency analyzer for mathematics, transforming an invisible repeating pattern into something measurable. Now we perform the measurement. The result is not usually the period itself. Instead, we obtain information that allows a classical algorithm to reconstruct the period. Once the period is recovered, we plug it into the number theory we saw earlier, and the supposedly unbreakable lock holds open. There is just one catch. To run Shor's algorithm against real-world RSA encryption, we would likely need a quantum computer with millions of arithmetic physical qubits. Today's machines have only a tiny fraction of that capability and remain highly susceptible to noise and errors. We may still be many years away from a machine powerful enough to do this at scale. So we are safe now, right? Not necessarily. We are already in the middle of a silent cyber conflict known as Harvest Now, Decrypt Later. Hostile nation states and sophisticated threat actors know that Q-Day may eventually arrive. Today, they are collecting vast quantities of encrypted data as it moves across the internet. Classified intelligence, military communications, corporate secrets, financial reports. They cannot read most of it today, but storage is cheap. The plan is simple: capture the encrypted values now, open them later. By the time a sufficiently powerful quantum computer exists, sensitive information transmitted today could potentially become readable. The lock doesn't need to be broken now, it only needs to be saved. This threat has triggered the largest cryptographic migration in human history. Researchers are now replacing RSA with post-quantum cryptography. Instead of relying on prime factorization, many of these systems rely on extraordinarily difficult mathematical problems known as lattice problems. Imagine trying to locate the exact nearest point inside a geometric structure that exists in hundreds of dimensions. The mathematical tricks that power Shor's algorithm do not appear to solve these problems efficiently. Governments, banks, and technology companies are racing to deploy these new systems before large-scale quantum computers arrive. Shor's algorithm is one of the most extraordinary discoveries in modern mathematics. It proved that a theoretical equation could reshape global cybersecurity decades before the required hardware even existed. We are slowly leaving the classical era behind, and the stakes have never been higher. Thanks for watching. If this journey into the mathematics of quantum computing left you amazed, hit that like button, subscribe, and let me know in the comments. Would you trust your bank account to encryption that a future quantum computer might be able to crack? See you next time.